Hello everyone, my name is Hariharan SIVAKUMAR, and today I will be talking about my final O-REU project update, benchmarking the performance of machine learning algorithms for record linkage at different heterogeneity rates. My sponsor is the online REU program at Texas A&M, and I would also like to thank and acknowledge my supervisors, Dr. Kum and Maheen, who have aided and supported me throughout the course of this research project. The main motivation for this research project begins with the importance of record linkage in our day-to-day lives. With the ongoing COVID-19 pandemic in the world, record linkage plays an important and vital role in tracking COVID-19 data. Many hospitals and research centers contain records of COVID-19 tests of patients. However, they contain different but complementing data about the same patients. Therefore, by linking these different records or databases, it allows us to analyze the data to better comprehend death rates and understand COVID-19 health resource usage and other drugs and therapies. With these data resources combined, it allows researchers to study the illness pathway for patients with COVID-19 from primary to critical care. So what is record linkage? Record linkage is referred to as linking records or entities across various databases that have no unique identifier. The main challenge that is faced when observing data from different databases is heterogeneity, which means that the records can be different or they could have different attributes or characteristics. The main objective of the project is to determine how the heterogeneity rate can affect the performance of three different machine learning algorithms: random forest, dense neural networks, and support vector machines in record linkage. The performance of each of these algorithms will be evaluated using an F1 score and the percentage of manual review that needs to be done by a person. When coming across more than one dataset about the same person, there are common issues that we face. Some common issues that were frequently seen include changes in data, such as women altering their last name when they get married. Sometimes, the two or more records are not unique, such as two people having the same name or twins who could have the same address and even have the same last name, which can be quite confusing. Moreover, the data can have significant errors, like errors in date of birth or changes in first name, which can be caused by human errors, such as typographical errors. Also, the data can be expressed in a different manner, where nicknames are used instead of a first name. I began the process of heterogeneity generation by utilizing the benchmarking system, which is used to introduce the errors into the dataset. The errors were introduced at different rates, ranging from 0% to 60% in increments of 5%. These rates will help us understand how much of an effect it has on the algorithm's performance when there are more errors in the dataset. The types of errors that will be introduced are basic name and date errors. These are some of the errors that will be introduced, mainly dealing with first name and last name and the date of birth of the person. As seen in this picture, the benchmarking system will take the original dataset and introduce errors using the benchmarking system and create another dataset with the given errors. The dataset I used for this project was the North Carolina State Board of Elections data, which contains data on state elections and voter registration. This dataset can be downloaded from the given link in the slide. The picture below shows a snapshot of the dataset, which shows the different attributes of each person. Using the benchmarking system mentioned in the previous slide, the name and date errors will be introduced into this dataset at different rates, ranging from 0% to 60%. The machine learning models that are going to be trained and evaluated are random forest, dense neural networks, and two types of support vector machines, linear and radial. The dataset is going to be split into a training dataset and a testing dataset. The algorithm will be altered and tuned after running it on the training dataset. Once the algorithm is ready to go, the model will then be used on the test dataset to make sure it is implemented correctly. As seen here, we have two datasets, the original and the dataset with errors after the heterogeneity generation, using the benchmarking system. Using each different model that was trained and tested, each record from each dataset will be compared and classified as matched, unmatched, or under manual review. After running each algorithm on the datasets, the performance of each model was first evaluated using an F1 score. A F1 score is used to measure the accuracy of a test by using both precision and recall. Therefore, higher the F1 score, the more efficient and accurate the algorithm is. As seen in the graph, with the x-axis being the different rates and the y-axis being the F1 score, overall Random Forest had the highest F1 score out of all four algorithms. Random Forest's F1 score drops at a lower rate than the other models as the error rate increases. Neural networks drop from 99.5% to 97.9%, and the linear support vector machine drops from 99.5% to 97.6%, while the radial support vector machine drops from 99.5% to 98.6%. The second evaluation done was to measure the percentage of manual review that needed to be done for each model. Manual review is basically the records that need to be manually inspected by a person. In general, the more manual review that needs to be done, the less efficient the algorithm is. As clearly seen in the bar graph, with the x-axis again being the heterogeneity rate and the y-axis being the percentage of manual review, the support vector machine linear had the highest percentage of manual review that needed to be done. The random forest ranged from 7.9% to 16.8%, while the neural networks ranged from 9.8% to around 16.4%. The radial SVM varied from 8% to 16.4%. In conclusion, to summarize the results, datasets with more errors cause a decrease in the algorithm's performance. But as seen from the data, the random forest model was more robust to error, as its performance decreased less than the other models. Although the random forests had the best F1 score, with 99.1% on average, it was quite marginal, as the random forest model was only 0.3% greater than the neural networks and 0.4% greater than the support vector machines. In this experiment, a simple neural network was used, but if the neural network was trained with a stronger training data set, it would have come close or even outperformed the random forest in terms of being efficient. However, in terms of percentage of manual review, the random forest model performs much better than the two other models, as the amount of review required was 2.1% less on average than the other models. This shows that random forest should be utilized for record linkage as it deems to be most effective than the other two algorithms that were tested in this experiment. Thank you.